Hi, I'm David, and today we'll be going through a chemistry paper 4 crash course. Alright, so every year in paper 4, they repeat the similar questions. There are many questions that are repeated over and over again in different forms. So the whole purpose of this crash course is to go through all of these questions and master them so that you will be able to easily get at least maybe 30 marks, 40 marks guaranteed for paper 4. Right, so let's move on to the first point, thermostability. Oh yeah, before further ado, I would like to recommend that you go to this website called lecturemate.site/notes.html. This is because I'm a major contributor to this website and I have uploaded a lot of notes here. Most of the content for this presentation comes from this A2 level cheat sheet, and I recommend you to have this open in another tab while I'm going through all of the content. Alright, so back to our presentation. Okay, for thermostability, basically you can count on this coming out every year in different ways. So the way you answer it is basically almost always the same. First off, you have to state the trend. Going down group 2, the thermostability increases. And why does it increase? Because the charge density decreases. Okay, what does this mean? Because going down the group, let's say that this is group 2, going down the group, charge remains the same. They're all always +2. This is +2, this is +2, this is +2. But then the ionic radius increases, so the +2 charge is spread out over a much bigger surface area, causing the charge density to decrease. Because the charge density decreases, it causes the nitrate and carbonate ions to be less polarized. When the nitrate and carbonate anions are less polarized, that means that this bond here, the C2O bond, cannot be broken as easily. So the carbonate doesn't decompose as easily into carbon dioxide and oxide, making it much harder to decompose group 2 carbonates. Alright, with that out of the way, let's go to number 2, ionic equations. Okay, so this is one of those questions where it's actually quite easy, but you still see a lot of people making a lot of careless mistakes. So I figured that the most error-proof way to solve this is to follow these 3 steps. Number 1, you balance out the electrons. Number 2, cancel out similar stuff. And number 3, rewrite equation. Okay, so for an ionic equation, the electrons must cancel out on both sides. 2 electrons, 5 electrons on this side. The lowest common multiple is 10, so we need 10 electrons here, 10 right over here. Alright, so in order to achieve that, we have to multiply this whole thing by 5 and multiply this by 2. Alright, so we basically get 5H2O plus 5SO3 equals 5SO4 plus 10H plus 10 electrons. The other side we're going to multiply by 2. Sorry, the lower equation we're going to multiply by 2. 16H plus 10 electrons equals to 2Mn2 plus 8H2O. Okay, so now we've balanced out the electrons. We got 10 electrons on the right hand side, 10 on the left hand side. What we need to do now is to cancel out the similar stuff. Of course, we can cancel 10 electrons. Now H plus, we cannot exactly cancel it out because we got more H plus on left hand than right hand side. but we can deduct 16H plus by 10. So we deduct this, and we get 6H plus. So we can't cancel out H plus entirely, but we can do it like in a way we can cancel it out partially. We can also cancel out H2O partially to get 3H2O here. So lastly, we can rewrite our entire equation: 2MnO4 plus 5SO3 equals to 5SO4 plus 2Mn2 plus 3H2O. There we have it. We have our full ionic equation. Alright, so let's move on to the next one, transition metals. Alright, so for transition metals, this is very much a memorizing game. I put everything out neatly in this table, so I really recommend you going to this website, reading this table and memorizing everything. So because this is a memorizing game, we'll just have to fill in all of the formulas here. And unfortunately, there is no shortcut to memorizing these formulas. You just have to read the table, try to understand it, and memorize it as well as you can. But there is actually one thing I would want to note here. For cobalt hydroxide, in some past year papers, you will just see it written as cobalt hydroxide. You won't see the water ligands. If you see this, don't worry, because it is the same thing. Just COOH2 and COOH2H2O4 are just different ways of writing the same stuff. Why? Because cobalt hydroxide solution, when you have cobalt hydroxide in water, it will naturally form water ligands. But sometimes, for the sake of convenience, we leave out the water ligands when writing out our equations. So if you see a transition metal equation and you only have COOH2, don't worry. It is just the same thing as COOH2H2O4. Okay, so now we go try to state the color and the state of cobalt species. So there is actually no in terms of memorizing the color, there isn't really a specific spatial method that I know of. But for memorizing the state, there is a very easy method. Alright, look here. For anything that it does not have hydroxide, it is a solution. For anything that has hydroxide, it is a precipitate. So CONH3 is brown solution. COCl4 is a blue solution, and COOH2, OH we have hydroxide, so that means it's a precipitate. It's a blue precipitate. Now the type of reaction. Alright, transition metal reactions are almost always ligand substitution. Basically this, if you don't know what it is, just write ligand substitution. There's a very high chance you'll be correct. But there's actually one thing that I want to get to later on. Alright, here technically this can be considered ligand substitution. Why? Because the OH is technically displacing two of the water ligands. However, Cambridge always wants you to be specific. Here a precipitate is being formed, so instead of ligand substitution, you're supposed to write precipitation. So basically, if it's possible to actually write precipitation, you use it. Not possible, you just put ligand substitution. Okay, so in some very rare circumstances, you actually have a redox reaction in transition metal. For a redox reaction, usually it would be something like, usually it will involve basically iron complex ions. Maybe you have iron H2O6 2 plus that becomes iron when maybe you can have something like this. If you get something like this, then yes, it is a redox reaction. In other words, it is almost always ligand substitution. When you have a precipitate forming, even though it's ligand substitution, they want you to be more specific and you should write precipitation instead. If you come across a scenario where you have a transition metal that is very obviously being oxidized, like here iron 2 to iron 3, then you have to write a redox reaction. So Linisk, I hope that answers your question. Okay, so next would be the Born-Haber cycle. Okay, so for the Born-Haber cycle, this is another one of those questions that is actually not so difficult, but very easy to make careless mistakes. So for Born-Haber cycle, what I've done is to list out basically all of the enthalpy changes that are involved. And if you include all of them, you should not miss out anything because it's quite easy to miss out one or two. Okay, so first off, we need to have the atomization of the metal. So the metal in this case is silver, all right? But enthalpy change of atomization. Look, we have Ag2, we have two silver atoms. So we need to multiply the enthalpy change by 2. Okay, so next we have to go on to the ionization energy of the metal. Ag in this case is only oxidized to Ag+, so we only need the first ionization energy. So we just 731. We also need to multiply it by 2 because it's a stoichiometric, because we have 2 silver atoms. Now we go on to the non-metal, which in this case is oxygen. Okay, so we need the enthalpy change of atomization for non-metal and the electron affinity. But for the enthalpy change of atomization of non-metals, it can get a little bit tricky, and I mean this is important, so listen up. Sometimes in the table here, they'll give you something like enthalpy change of atomization of, let's say, of bromine. And then other times they'll just give you the bond energy, like in this case you get O2, O2O. So what's the deal? Okay, in order to atomize a non-metal, what you have to do two things. First off, you have to vaporize it, you have to convert it to gas. Then you, after you're done vaporizing, you have to break the bonds. So when your non-metal is a liquid or solid at standard state, like for example bromine in standard states is actually a liquid, what you actually have to do is you have to heat it up to vaporize it, to convert the bromine to gas. Then after you're done vaporizing the bromine, you break the bonds, you break the Br to Br bonds, you break these bonds. So the enthalpy change of atomization of a non-metal is actually the enthalpy change of vaporization plus the bond energy. It is actually this. But what if your non-metal is already a gas at room temperature like oxygen? In that case, you don't need the enthalpy change of vaporization. You only need the bond energy. That's why they only gave the bond energy here. So next time, do not get confused between enthalpy change of atomization of the non-metal and the bond energy of the non-metal. So any questions about this? Can we write the precipitation as, oh, this one is actually going back to the previous question. Can I answer that later on after I'm done with this question? And oh yeah, I want to see what Billy has to say. All right. Oh, can I repeat this? Okay. For non-metals, okay, for non-metals like bromine, oxygen, the enthalpy change of atomization is equal to is basically the enthalpy change of vaporization plus the bond energy. Let's say we have bromine. Bromine is a liquid at room temperature. To atomize bromine, we have to heat it up. We have to vaporize it until it's all in a gas. Then we break the Br to Br bonds to get the individual bromine atoms. So what I was basically talking about just now is sometimes when they give you this table, they will give you they don't give you the enthalpy change of atomization, they just give you the bond energy. So this is because some elements like oxygen, in standard states, they are already present in a gaseous state. You don't have to vaporize it, so you only need to factor in the bond energy. You don't need to vaporize it, so they don't give you the whole enthalpy change of atomization of oxygen. They just give you the bond energy. Okay, so Billy, do you understand it now? All right. Okay. Okay, right. I was about to get to that. Thanks for asking. It's a great question. Okay, so back to this. So just to recap, we have this is the enthalpy change of atomization of Ag, and this is the first ionization energy of silver of Ag. So now we have to go to oxygen. So oxygen, well, it's already in gaseous state, like we don't have to vaporize it. We just need the bond energy. We just need the bond energy. So for the bond energy in this case, yeah, which one do we use? This or this? Well, we have to use the first one, the double bond. Why? Because normally oxygen will exist in O double bond O. So we actually will have to break both of the double bonds in order to get the individual oxygen atom. So we do, but one thing to note here is for O double bond O, we have to divide 496 by 2. Okay, we have to divide 496 by 2. Why? Because the energy put in to break this double bond, we actually get 2 oxygen atoms out, but we only need 1. So the only way is to divide 496 by 2. Alright, get it? So Roy, did I answer your question? Now for using O single bond, or there are some very specific cases where to use that in organic chemistry, but anyway, that is not really, yeah, that is not really related to Born-Haber. So yeah, okay, we already have the atomized oxygen. So the next thing is we need the electron affinity. Here is O negative 2 oxide. So we have negative 141 plus 798. Okay, so this is just to digress a little. One thing I noticed, I noticed I noticed that some people actually do this when, let's say, it's plus negative 141 for first electron affinity. Instead of, they just do something like this, minus 141. Now, this is not wrong, right? It's not wrong to do this, but the problem is that you can get confused. It can be a little bit confusing, and you can make careless mistakes. So what I always recommend is adding the sign within the bracket, like 2 bracket plus 285 plus 2 bracket plus 731. I always recommend writing it out this way so that it is easier to see all the positives and negatives, so that you're less likely to press the wrong number into the calculator or anything. Okay, so now if we have enthalpy change of atomization and ionization of silver and oxygen, the next thing we need is the lattice energy. Now in this question, we don't have the lattice energy. We have to figure that out for ourselves. Never mind. So once you have the lattice energy, then all of this added up equals to the standard enthalpy change of formation, which is negative 31. Alright, any questions? Alright, I can see Shrinish typing. No, alright. Alright, so now as a quick exercise, I want all of you to find delta H, the lattice energy. I've already written out all the numbers. Just a simple method of using the calculator. Right, type the answer in the chat. I want to see who is the fastest. Negative 2968. Did everyone else get negative 2968? Alright, so I guess that is the answer. Right, so with that out of the way, alright. Now before I go into lattice energy, let me go back to answer Roy's question about precipitation as acid base. I'm not really sure, but I would not recommend doing that, because the thing is, when you're answering a question, you want to be as specific as possible. Clearly, that is a precipitation reaction. You don't want to answer something weird like, okay, but anyway, just for interest sake, let's see if it's really acid base. Let's take a look at it. Okay. I think in this case, Roy, sorry about that, but I think writing acid base I think it would be very wrong, because Acid base would mean that you have an acid reacting with an alkali to produce salt and water. Cobalt, like aqueous cobalt, is not really what we would call an acid. Sodium hydroxide is definitely a base, but aqueous cobalt is not what people usually consider to be an acid. So it's not really an acid-base reaction. It's more of a precipitation reaction. Alright, so Roy, does that answer your question? Okay, Linesk asked about redox. Okay, this one I did not write it. I did not write it down in this slide. Wait, give me a moment to check whether it's. Okay, so sometimes when you have iron 2 or iron 3 complex ions, like for example iron 2 complex ions, it can oxidize into iron 3 plus. So in this case you can say redox. Basically when you have an iron 2 complex ion that oxidizes to iron 3 plus, or iron 3 plus reducing to iron 2. So Linesk, does that answer your question? Yep. And also thanks for asking that. It was a good question. I mean, personally, yeah, I didn't even think about mentioning that until you brought it up. So thanks for reminding me. Okay, so now okay, for Dua, yeah, I am recording the presentation and I will try to upload it to Google Drive later on. Right, okay. Okay, so now let's go on to lattice energy. So lattice energy is actually another one of those questions that is always going to be repeated, although in very different ways. But the basic way you answer it is the same. Number one, you have to mention the charge density, and then you also have to talk about the ionic radius. Okay, so let's look at Ag2S, Ag2O, and Ag2Se. So Ag is the cation's the same. The difference here is the non-metal, the anion. So let's pull up our periodic table. Alright, so as we can see quite clearly here from our periodic table, oxygen is right up top, followed by sulfur, and followed by selenium. Right, alright, I'm back. Sorry, I was lagging out a little bit. Okay, so oxygen is right up top, followed by sulfur, and then followed by selenium. So oxygen actually has the smallest ionic radius, and therefore because it has the smallest ionic radius, it has the highest charge density. So we got that first point in. We already talked about the charge density. So we just say the charge density decreases down the group. Okay, so why does it decrease? Because the ionic radius increases. Alright, we got the second point. So what's next? Then we have to go to the ionic bonds or the we we talk about the ionic bonds now, or if you don't like the word ionic bonds, you just change it to electrostatic forces. Same thing. So you say that, therefore, the electrostatic forces between the Ag plus cation and the group 16 anion get weaker and weaker down the group. So the lattice energy decreases. In some mark schemes, I've seen them do something that I think is they also answer the last point rather than talking about ionic bonds. They say it this way. They answer it like this. This is also another way to answer the last point. And what's the logic behind it? Alright, because when the anion is bigger, the outermost electrons are actually further away from the nucleus, and we actually know that the ionic bond is due to electrostatic forces between the electrons and the nucleus. So when the ions are bigger, of course the ionic bond is weaker. So another way to answer is, rather than just saying ionic bonds get weaker, you be more specific. They approach, cation and anion approach each other less closely. That is another way to answer this. So right, do you have any questions? Right, if no questions, then I'm going to move on to the next one, Gibbs free energy. Okay, so Gibbs free energy is quite, basically the basic equation is very simple. It's just Gibbs free energy equals to H minus T delta S. So every year there will be definitely a question asking you to relate Gibbs free energy to feasibility. Okay, so just to get it out of the way, don't get confused. When G is more negative, reaction more feasible. G is more positive, the reaction will become less feasible. It's like opposite, so don't get it mixed up. So they'll always ask you a question on when the temperature increases or when something else changes, does the reaction become more or less feasible? Okay, so in this case, we actually have to look at the standard enthalpy change and the entropy change. Entropy change was in a previous sub question, and sorry, I forgot to write it here. The entropy change is actually something like plus 5. I mean, it is a positive number, so let's just say plus 30. Okay, so now let's take a look at this from like a very maths point of view. G basically equals to 22.6 minus T times the standard entropy change, which in this case is 30. Alright, one thing to know, when you calculate entropy change, this thing is always in joule per Kelvin per mole. It is not in kilojoule it is just in joule. So for your T, you actually have to divide 30 by 1000. So it's 22.6 minus T times 0.03. not 22.6 minus T times 30. Do not make that mistake. Alright, so this is our equation for G. So now let's try to see what happens when the temperature increases. So the temperature is always going to be positive because we are calculating in Kelvin. So let's say that T is 500 K, right? Let me get out my calculator. G equals to 7.6. Now, what happens when we increase the T to 1000? We get negative 7.4. Alright, now let's get crazy. Let's say we're doing this at 5000 Kelvin. We get a whopping negative 1 to 7.4. So as you can see here, when you keep increasing the temperature, what you're actually doing is you are causing negative TS. You're causing the Gibbs free energy to become more and more negative. And when G is more and more negative, what does it mean? It means that the reaction is becoming more and more feasible. It will happen more and more easily. So this is why many experiments in the lab, when you're doing it, it always helps to heat it up a little bit, especially for organic, because it makes the Gibbs free energy more negative. So it makes the reaction more feasible. So the reaction would start occurring more easily. Right, so any questions for this? Okay, can we not calculate G in joules instead of kilojoules? You can. Okay, one thing to note is this one if the question specifies that it must be in kilojoules, you have to give in kilojoules. If the question specifies you give in joules, then actually basically you just follow what the unit that the question gives you. If the question does not give you a unit, I heavily recommend giving it in kilojoules, because that seems to be the standard for Cambridge. But if it tells you to give in joules, go ahead. So Roy, does that answer your question? Right, so now let's move on to also Gibbs free energy. So now, using what I've explained earlier, I want you to calculate the Gibbs free energy for this thing. I give you about 3 minutes to do this, using what I have explained earlier. Concentration of iodide to the power of something else, the power of y. We don't know what the power is, and this is what we actually have to calculate in the red equation. Okay, so here we see that the concentration of iodide is the same, is 0.02, 0.02. Here the concentration of Fe3 plus changes, so this experiment 1 and 2 is we can use it to figure out what X is. Okay, so when concentration of Fe3 plus triples from 0.04 to 0.12, then the initial rate, it also triples. You want to verify it, you just take out your calculator, you do 7.92 10 to the power negative 4 divided by 2.64. 10 to the power negative 4. Basically, you will get 3. So in other words, what you always do is you find like 2 experiments where one of the concentrations remains the same. Then you divide the rate of reaction for these two and for the reactant whose concentration changes. So as we can see here, when Fe3 plus, when it triples, your initial rate also triples. So what does this mean? This means that x is 1. Okay, it means it's raised to the power of 1. X here is 1. Okay, so why? Because let's say if x is 2, right? Let's say x is 2. When concentration of Fe3 plus triples, initial rate will increase by 9 times. 3 squared equals 9. If x to the power of 3, initial rate will increase by 27 times. 3 power of 3 cubed is 27. But x is 1. So when it triples, initial rate also triples. 3 to the power of 1 is 3. So basically, does anyone have any issues with this? You have, please type in the chat. Okay, so Billy, what is it about the iodide part that you do not really understand? Because I have not calculated the power for iodide yet. Okay, for now I have already calculated the power of X. Like we know Fe3 plus is raised to the power of iodide is raised to the power of Y. We haven't calculated Y yet. So now let's go and calculate Y. Okay, so now you might be thinking, okay, we have a problem now. Yes, for these two iodide, the concentration is different, but the Fe3 plus concentration is also different. So how do we deal with this? The way we deal with it is quite easy because we already know what Fe3 plus is raised to. We know X. So we can just cancel out Fe3 plus. So power of negative 4 and divided by 0.12. We cancel out, we remove the Fe3 plus by dividing the initial rate by Fe3 plus. In this case, Fe3 plus is the power of 1. It's raised to the power of 1, so we just divide by 0.12. But if we have something like K times Fe3 plus square times iodide then this 0.12 has to be like raised to the power of 2, but here it's not really the case. We know that x is 1 raised to the power of 1, so this one we just keep it as 0.12. So from this we get 0.0066. Okay, so for the next one, experiment 3. Same thing, we remove out Fe3 plus. Get a 0.02638. Okay, so what we can see here is that for iodide, the concentration doubles. And so what happens to the rate of reaction? Okay, so let's try to divide this by this. Let's see what happens. When iodide doubles, the initial rate quadruples, increases by 4 times. To the power of y equals 4. So, but from this, it is quite easy to see that y is 2. So our rate equation is K times Fe3 plus times iodide square. Right. Any questions? Right. If no questions, then I'm going to go into calculating the rate constant. So the rate constant, okay, just let me move this to the side. Sorry, let me move this to the side a bit. Move this to the side. Okay, the rate constant. We already know the equation is K times Fe3 plus times iodide square. So to find the rate constant K is quite easy. We just select any experiment. I'll just go with experiment 3. And we'll divide it by 0.04 squared. Times 0.08. Okay, so why do we do this? Because the initial rate, basically, the initial rate is equal to K times concentration of Fe3 plus and concentration of iodide squared. So if we can just take the initial rate, divide by this to get K. It's simple math, and that's exactly what we are doing here. So we get 2.11 10 to the power of -3 divided by times. So we get 16.48. Alright, but now this is not enough. We need another very important thing about the rate equation is that we need the units of the rate constant. Okay, so the initial rate, as you can see here, is given in mole per decimeter cube per second. Fe3 plus and iodide are given in mole per decimeter cube, but iodide here is actually, as you can see, it's squared. So basically Fe3 plus times iodide squared, you basically get mole cube decimeter -9. So the rate constant is, the units are supposed to cancel this out to form mole per decimeter cube per second. So in that case, the units of K have to be mole -2 dm 6 second, because this is the only way we can get an initial rate with this unit. So do you all understand this part? Right, so therefore K equals to 16.48 times, sorry, that K equals 16.48, and with the units mole -2 is dm6 per second. Now this is one very important thing. Sometimes the mole they don't give in second, they'll give in per minute or per hour. In that case, the units of K, you just change this to per hour or per minute. Don't make the careless mistake of not checking your units. Alright, so with this out of the way, now let me go into K, the relationship between rate constant and temperature. Okay, so let's imagine, let's just do what I call a thought experiment. You add 0.04 moles per decimeter cube of Fe3 plus and 0.02 moles of iodide into a beaker, and then add maybe 200 K. So your initial rate is maybe 1 mole per dm cube per second. Now you do the same experiment, also is 0.04 moles and 0.02 at 600 K. You get 3 mole per decimeter cube per second. You get initial rate that this. Now you do it. Now we go crazy. We do it at 1000 K. Then our initial rate becomes 20 mole per decimeter cube per second. So as you can see here, we are keeping the concentration of this thing, Fe3 plus and iodide, the same. We are not changing it. But what is causing our initial rate to keep changing? Well, the only explanation is that K, the rate constant, is changing. So as we increase the temperature, the rate constant also increases. And that is why usually reactions occur faster when you heat it up, even if they are kept at the same, even if they are actually kept at the same initial concentration, because you are increasing the rate constant, you are increasing the K, so you make the reactions happen faster and faster. So whenever the question asks you something like, how does K increase, what happens to K as temperature increases, then you have to say K increases as temperature increases. If they ask you to draw a graph, you draw an exponential line like this. You draw an exponential line like this. Right. Any questions with this step? With this rate equation subtopic? Okay, with no questions, then let me move on to the next part, the rate determining step. Okay, now how do we determine the rate, the RDS? Basically, the RDS is actually the slowest step in the series. Like we have This reaction occurs in 4 steps, and one of them is the slowest, is the bottleneck. One of them is the slowest, is the bottleneck. So how do we determine which one is the bottleneck? Okay, there are two types of RDS questions. There's one type where they are very cruel. They just give you the steps and they with no clues. You have to figure it out for yourself. There's another type where they are very nice. They give you the clue. So I will go into the one with the clue first. So in this case, they say that it is first order with respect to iodide, and first order with respect to H2O2, and zero order with respect to H+. So what does this mean? This means that the rate equation basically equals to K times iodide power of 1 times H2O2, also power of 1, and H plus power of 0. Anything power of 0 is anything power to the raised to the 0 order is not included in the rate equation. So basically the rate equation is K times iodide times H2O, concentration H2O2. Okay, so now let's take a look at all of these steps. Step 1 is 1 mole of H2O2 plus 1 mole iodide equals to this. Step 2 is this one, react with H plus. Okay, so we know that H plus is not involved in the rate equation, so it cannot be step 2. Cannot be step 2. So we have to look at all of the steps that are before step 2. Okay, in this case it's very easy for us. There's only one step before step 2, and that is step 1. So this is the rate determining step. Why? Because it has 1 mole H2O2 reacting with 1 mole of iodine. Okay, so now let's try to make this question a bit harder because I want to show you a particular concept. Okay, but what if, let's say, instead of being first order with respect to iodide, and zero order with respect. Okay, what if it is a second order with respect to iodide and first order with respect to H plus? Okay, now this is going to make this question a lot harder. So we have 1 mole of H2O2 reacting with 1 mole iodide in step 1, and in step 2 it reacts with H plus. Okay, but this still doesn't satisfy our rate equation, because step 2 is has 1 mole of H plus reacting with 1 mole of H2O2 and 1 mole of I. Alright, because IO is formed from these two, we can consider it to be like first order with respect to this, first order with respect to iodide as well. So still doesn't answer our question because we want it to be second order with respect to iodide. So now let's look at step 3. In step 3, HIO reacts with iodide. Alright, HIO is formed from H2O, 1 mole H2O2, 1 mole iodide, and 1 mole of H plus. And it reacts with iodide again. So therefore, it already it's made up from 1 mole iodide here, reacts with iodide again, iodide. Therefore, iodide now is second order. So step 3 is our RDS. Why? Because step 3 is first order with respect to H plus, because of HIO here is first order with respect to H2O2, and it is second order with respect to iodide, because iodide reacts here and it reacts again, it reacts 2 times. So step 3 will be our rate determining step. Right, any questions? 1990. Okay, so okay, I'll try to explain it give me a moment. I'll try to see how I can explain it in a way that's a bit simpler. Okay, here the initial rate of reaction is second order with respect to iodide, first order with respect to H2O2, and first order with respect to H plus. Let me change this thing so that it's like easier to see. So which step is the RDS? Okay, step 1, you have 1 mole of H2O2 and 1 mole of iodide, so it's not the RDS. Step 2, you have 1 mole of H plus times 1 mole H2O2 times 1 mole of iodide. Why do I times 1 mole H2O2 and iodide? Because it reacts with IO, which is formed from the reaction in step 1, which is a reaction between 1 mole of H2O2 and 1 mole of iodide. Alright, so we look at step 3, where it's HIO. HIO is formed from 1 mole of this, 1 mole of H2O2 and 1 mole of iodide, and it reacts with iodide again. So you see iodide is involved in the reaction twice. There are 2 moles of iodide involved. So therefore iodide is second order in step 3. H2O2 is first order, and H plus is first order. So therefore step 3 is the rate determining step. Linus, does that answer your question? Alright, if it doesn't, then later on at the end I can try to see if there's a way to make it simpler. Okay, so now we go on to the next. Now this is where they can be a bit cruel. You see here they don't give any description, they just slap the 2 equations here. So which one is the RDS? For this one we have to use logic to see how easy it is for the 2 reactants to react with each other. So basically, if it's a positive and negative reactant, the reaction will occur very fast. It'll be very easy because positive and negative attract. But what if it is a negative and negative on positive and positive? Oh, that one will be a very slow step, because the positive and positive and negative, they will repel, so it's very hard for them to react. They will react very slowly. Now, for positive to neutral, negative to neutral, or even neutral to neutral, it's sort of in between. It will not happen fast or slow. It's like it will happen at a moderate speed. So in these 2 steps, the first step is the reaction between Cu2 plus, a positive, and iodide, which is a negative. So when they react, so of course it's a very fast reaction, it's positive to negative. Second step is between a neutral and a negative one. This one will be slower, so therefore step 2 is our rate determining step, is the slow step. Right, does anyone have any questions? Everyone understands this? Okay, so now let's move on to number 9. Alright, so for number 9, it's about finding the other possible products when in organic reactions. So sometimes it can be quite confusing, like they'll give you just a random molecular formula and you have to find what the additional product is. But don't worry, this one is not actually it's not as difficult as it seems. You have to look at the benzene here. Look at the benzene ring here. 1, 2, 3, 4, 5, 6, 7. Yes, 7 carbons. Here is C14H14OS. So as you can see here, the number of carbons in doubles. So what does that tell you? That tells you that there is an extra benzene. So in other words, basically when you're asked to give other additional products, you will try to just try to find out how many additional benzene rings are added by comparing the number of carbon atoms. Alright, any questions? Right, no questions. Let me move on to the next, hydrolysis. Okay, so this is also a very common question where they will give you the just one organic compound here, and you have to hydrolyze them. You have to break them up. Imagine what they look like when they're hydrolyzed with acid. So the first step is to find all the amide and the carboxyl bonds. You have one bond here. Okay, this is obviously a carboxyl bond. Now let's look at this bond. This bond, if you actually think about it, it's just a regular amine. It's not an amide or a carboxyl, so we don't cut anything. Now what about this? This one is actually a carboxyl. This is actually an amide bond as well. N double bond O. So we also cut this. So therefore, our products are quite clear already. We have ethanol here with whatever organic compound this thing is, and we have another organic compound here which has basically these 2 rings, but it has NH instead of being connected to this. Any questions? Oh, okay. Basically, when we are asked to hydrolyze hydrolyze an organic compound, we look for 2 things: the amide bonds and the carboxyl bonds. Okay, this bond is a carboxyl. We cut the bond. This bond is not an amide, it's an amine. Why? Because the N is not directly connected to a double bond O. There's no double bond O here or here. This one, the N is directly connected to a double bond O. So we cut this one. So now if we want to draw out the products, we just draw ethanol here. And here we just draw it connected to OH. Here we draw it connected to here we draw it connected to OH, and the N we make it connected to hydrogen. So there we have it. We have our 3 organic products. This one with N connected to hydrogen, this one with OH connected to the C double bond O here, and lastly this one which is basically ethanol. Right, understand? Shrinesh, okay with this? Number 12 is comparing the difference in reactivity between chloroethane and chlorobenzene. So a lot of things you get will be in organic chemistry will be about the benzene ring. So the benzene ring, one characteristic is that it is electron withdrawing, and it has the delocalized ring of electrons above and below. So what happens is with the delocalized electron ring is that the p orbitals will overlap with the one in the hydroxyl group in OH. So let's say you're comparing the reactivity between just chloroethane and chlorobenzene or ethanol and phenol. The benzene will always be more stable. Why? Because the p orbitals of Cl will overlap with the delocalized electron ring. So this will strengthen the bond, and this will make it more stable and therefore less reactive because the bond cannot be broken as easily. Alright, so any questions? Okay, so next we go on to drawing the electrochemical cell. Okay, so for electrochemical cell, there is actually a very specific format. You cannot, you have to draw two cells like this, okay? And in one cell, you have to draw the electrode. Okay, so so we have the Fe3 plus Fe2 plus electrodes on one side. Both of these are solution. We have Fe3 plus here and Fe2 plus. Fe3 plus solution and Fe2 plus solution. Both at 1 moles per decimeter cube. And we add a platinum electrode. So in the other side, we have chlorine to chloride. But chlorine is a gas, so we actually have to draw a gas supply like this with a chlorine gas. We have a chlorine gas supply here and 1 mole of chlorides. 1 mole per decimeter cube of chloride. And within the gas supply, we add a platinum electrode. So now we connect the two electrodes using a wire which is connected to a voltmeter or a galvanometer and a salt bridge. So the mistake I see a lot of people making is they forget to label. They forget to label the salt bridge. This one you have to label is the salt bridge. And they also forget to specify that the Fe2 3 plus and Fe2 plus are both at 1 mole. This is very important. And lastly, in this question, we don't have to state the conditions used, but normally, because this question is a bit unusual, you have to state this is at 1 atm, 298 K. And that's how you get the full 4 marks from drawing the electrochemical cell. Okay, so next, number 14, comparing acidity and basicity. So we have about a few more left. Okay, acidity and basicity. So you will get these questions. These are 4-mark questions. These are 4-mark questions. So we better not get this wrong. So to answer it, this question that will be about comparing basicity. Later on, this will be about comparing acidity. Okay, so for acidity and basicity, how do we compare it? First off, we have to start by thinking about what a base is. A base is something that accepts H plus ions, so it must be something that is electronegative. That's why it can accept positive H plus. All right. So here we can say that C2H5 NH C2H5 is a stronger base than NH3. Why? Because the C2H5 groups here are electron releasing, so they release electrons towards the N atom. It causes it to be more negative, so it accepts the H plus more easily. Then next, we have to talk about why NH3 is a stronger base than C2H5NH, than this thing, C2H5NH, COCH3. Okay, because the p orbitals of Cn and O, what they actually do is the p orbitals all overlap. So the electrons on N, they don't stay on N, they move around here. So this causes the negative charge on N to be lower. So when the negative charge on N is lower, it becomes less electronegative. So it does not accept H plus as easily, so it's a weaker base. So basically, when you're answering these questions, you have to do four things. First, you have to list out which is the most basic to the least basic. And I actually put up how to compare strengths of acids and bases in this article here. Then after you are done listing from most basic to least basic, then you have to do three things, sorry. You have to explain why this is more basic than this, just as we did just now. Then we have to explain why NH3 this thing is more basic than this, which we also did. Then what's the last mark? Last mark is we have to talk about what it means to be a base, which is to accept H plus ions. So in this case, one thing I always recommend is rather than just saying base means to accept H plus, you work it into one of the explanations. So in this case, I worked it into the first explanation by talking about how it releases electrons towards the N atom so that it accepts H plus more easily. So in other words, first you list out most basic to least basic. You talk about why this is more basic than this, and this is more basic than this. And then you work in the definition for a base into one of your explanations, like I did here. For acids, it is more or less the same thing. But for acids, bear in mind, now it's about being more able to release the H plus rather than accepting the H plus. So in this case, the O atom has to be less negative, not more negative. Okay, so we move on to our last field, which are H and MR spectrometry. So far, does anyone have any questions about acidity and basicity? Okay, what's the difference? The galvanic and an electrochemical cell. That one, okay. An electrochemical cell and a galvanic cell are basically the same thing. It's just two different words for the same thing. The only difference will be electrolytic cell and galvanic cell, because electrolytic cell is where you have where you're trying to do electrolysis. Now this will be different, but galvanic cell and electrochemical cell are just the same thing. They're just two words for the same stuff. Linus, does that answer your question? Okay, lastly, H and MR. H and M. So you get questions on why you have to use what happens if you use D2O, and what happens if you use CdCl3. Okay, so for D2O, what happens if you... First off, I need to explain what D2O is. Like, everybody should know what H2O is. It's just two hydrogen connected to an oxygen, water, H2O. D2O is the same thing because deuterium is basically just an isotope of hydrogen. So basically it's like deuterium water. It's like water, but instead of hydrogen, you have an isotope of hydrogen called deuterium. So when you use D2O, what happens is that the hydrogen in all of the OH groups will be swapped with deuterium. You become this instead of this thing. So what is the effect? Basically, when you use D2O, all of the carboxyl groups, because they have an OH bond, as well as the alcohol groups OH, the spectrum will disappear. Like if you do the experiment without D2O, like probably you get a peak here because of OH. Then when you do it with D2O, the peak just disappears. So when you're asked to answer this kind of question, you just say the COH peak or the OH peak, depending on what molecule they give you, disappears because the H atom exchanges with D. Alright, get it? Okay, now we move on to the last one, for H and M, CdCl3. Okay, CdCl3, why do we use CdCl3 instead of CHCl3? Okay, because in proton NMR, each of the different protons will... Man, something's wrong with my stylus today. They will all give their different peaks. All of the protons in the molecule will all give their peaks here. CdCl3 will not give any absorption peaks. But the problem is if you use CHCl3 as a solvent, then the solvent will start to produce a lot of annoying peaks that are like almost the same place as the peaks produced by the molecule that you are trying to test. So it becomes very difficult to figure out which peak is due to CHCl3 and which peak is due to the molecule you are actually trying to test. Whereas for CdCl3 is not a problem, because for CdCl3, the peaks that it will not give any peaks that are close to the peaks produced by the molecule. So whatever peaks you see are 100% from the molecule you are testing in your NMR machine. Understood? Any questions? Alright, so no questions, move on to transition metals. Okay, so for transition metals, I'm going to go into three things, which are number one, the splitting of d orbitals, number two, how you get different colors, and number three, explaining how complex ions form colors. Okay, so as everyone knows, there are 5 d orbitals. When ligands bind to a complex ion, they will raise the energy of these 5 orbitals. So if there are four ligands, 3 of them will be raised higher and 2 of them will be raised to a lower energy level. Because 2 of them will be raised to a lower energy level. If it's octahedral, let's say 6 ligands, then 2 of them will be raised to a higher energy level and 3 of them will be raised to a lower energy level. So how do you remember this? Well, you just remember that this is like in a T shape. T for tetrahedral. You see the logic behind this memorization technique. Like if someone uses Times New Roman font, they should be familiar to you. You see 3 on top, 2 at the bottom is a bit like you join it up, it's a bit like a T shape. So remember T for tetrahedral, and for octahedral you just flip it. 2 on top, 3 at the bottom. Okay, so now the next part, how do you get different colors? Okay, so sometimes you can have 2 complex ions that are octahedrally coordinated. Both of them have have 2 d orbitals raised to higher level and 3 raised to lower level, but yet the color is different, and the energy gap is different. Why? Because in M, maybe it is raised like this. In G, it is raised like this. So as you can see here, the overall shape is the same. You got 2 raised to higher, 3 lower, 2 higher, 3 lower. But in G, the 2 orbitals are raised to an even higher energy level than in M. So therefore the energy gap is different. So they absorb different frequency of light, and therefore the wavelength of the light photons they absorb is different. Okay, any questions? No questions? Okay, I'll move on. How do complex ions form colors? For this one, it basically comes out every year, and this is like with the transition metal reactions I covered just now. It is also a memorizing game. You just memorize this paragraph, and then it's kind of guaranteed for marks. First, the ligands form dative bonds with the transition metal ion, so they raise energy levels of the d orbitals. Then the orbitals, orbital splitting. Sorry, there is a typo here. Orbital splitting occurs to form degenerate orbitals, meaning the orbitals at different energy levels. Then electrons, they absorb light energy to move from the lower to the higher, and therefore the remaining light wavelengths combine to form the complementary color. Alright, so now this is our last one, buffer solutions. Alright, so for buffer solutions, I give you 2 minutes to read through the question. Alright, is everyone done with reading the question? Okay. Okay, so one thing is the pH of this solution is actually 4.51. This was actually in the previous sub question, but I accidentally cut that out. So pH is 4.51. So to answer these questions, we basically fall back onto this Ka, where Ka onto this Lee-Chatelain's principle. Ka equals to concentration of C6H5COO times concentration H plus divided by concentration of C6H5COOH. So basically we need to find the concentration of CH3COO negative and A plus, which is sodium benzoate, which is basically equivalent to concentration of C6H5COO of the benzoate ion. Why is this so? Because when we put this into the solution, almost all of it will dissociate into C6H5CO negative and A plus. It will split up. So the concentration of this one basically is equivalent to whatever concentration of C6H5COO and A plus that is in the solution. So we know the concentration of C6H5COOH because they already gave us the mass. So we just have to calculate number of moles and divide it by the volume. We also know the concentration H plus because they gave us the pH. So we can use that and the Ka to find C6H5COO negative. So to find H plus from the pH, basically pH is negative log 10 H plus. So concentration of H plus basically equals to 10 to the power of negative H. So in this case, it will equal to which basically equals to 3.09 times 10 to the power negative 5 moles per decimeter cube. Okay, so now let's find, so we have the concentration of H plus. Now we just have to find the concentration of benzoic acid. Okay, they gave us the mass already. So we just have to find the number of moles. Number of moles is mass over molar mass. So in this case, it's 1 divided by the molar mass of C6H5COOH, which basically is 1 divided by 122. Basically equals to 8.20 times 10 to the power of negative 3 moles. Okay, so now we got the number of moles of C6H5CO benzoic acid that they added, and thankfully the buffer solution is also 1 decimeter cube. It is also 1 decimeter cube. So instantly we know that this is they added 8.20 times 10 to the power of 3 moles per decimeter cube. So we have the concentration of this and we have the concentration of this thing. We just need to find the concentration of benzoate, C6H5COO negative. So how do we find the concentration of this thing? Basically quite easy. We just sub it. We just sub everything into the equation. Ka we know is 6.31. H plus we know is 3. Okay, so basically just use your calculator and try to do the math. Give me the concentration of C6H5COO negative. Type your answer in the chat. 0.0167. Did everybody else get that? Alright. Yep, everyone else got that. Okay, so I think that concludes our crash course for today. Everyone, thank you for coming and thank you for your attention. I will share the recording of this thing. I will share the recording of this thing with you later on. I think what I will do is I'll compile the recording and give it to the mods, and then maybe they can post it somewhere. Do you have any questions about A2 chemistry in general? Doesn't have to be the stuff inside here.